All right, I just remade the our mode board here onto a separate sheet, so it should be an exact replica. It was actually kind of a good thing to do because it reminded me that I plotted all of the like contact positions in the same place, and then when I drew the DRM for contact A, it was actually came out to like 198 instead of 194. That's because this is not an exact science. You're going to get things slightly wrong sometimes, especially because, you know, you've just got two little dots here and you're trying to make sure that this is exactly perfectly in line between the two and there's no tiny differences. So I actually fudged it to get it at exactly 194 just so it's representative between the two. But that's it does go to show that you're not always going to get exactly the same thing as somebody next to you working on the same problem. Usually the standards are, if something's within 5 degrees, it's close enough to be fine. I mean, it's going to fluctuate how far away your CPA is, but it's still ultimately showing the same basic information. Anyway, now that we have 2 sheets, what we're going to do is we're going to set up the vector triangles for each respective system that we use. For this one, I'm going to use the Navy system. And I think we're going to start there because it's kind of the easier one to visualize. And for the Navy system, we're going to use everything based off of the center of the scope. And we're going to build the triangles here. There's going to be multiple here because we're working with 3 different contacts. So to begin, we have our ER here. What we're going to need is our RM vector and our EM vector for each contact. We can create our RMs pretty easily based off of the information we already have, and doing so is going to give us EM. So how this is going to go, we're going to take one contact at a time. We now have the direction of relative motion for contact A and the speed of relative motion that we calculated technically on this sheet at the bottom using the speed scale right there. We're going to transfer that information onto this ER vector here by just filling in the blanks. We have R here, so we're going to remake the RM vector to be representative of this DRM we have right here. So firstly, how we do that is we plot out, we carry over the DRM. So we're going to take, zoom out a little bit. We're going to take our triangle, we're going to place it, and again, because we're doing the Navy version, technically I should have the parallel plotter, which is makes it fairly easy to just move it over here. But I don't have that with me, so we'll be doing we'll be using the triangles, but same difference. We line up the triangle so it's perfectly in line with the DRM of contact A. And now we're going to slide it down until it gets to the R of the ER vector. And then we're going to draw out our line here. Make sure we go in the same direction that the DRM is. So the DRM is 194 going this way, so the RM vector is going to go the same direction. Now, how we're going to set up the length of that line is we're going to use the speed of relative motion that we calculated in the previous videos. So if we come back here to our other paper, you can see that the SRM of contact A was calculated to be about 8 knots because it went 0.8 nautical miles in 6 minutes. So that gave us 8 knots of relative speed. So we're going to now make this RM vector 8 knots long. And remember, the scale we're using here is the 5-to-1 scale. So we're going to come to the 5-to-1 scale. We're going to measure out 8 knots. Right there. Then we're going to place that on the R. along the line. That right there is our M. So now we have our E to R, our course and speed, R to M, the relative motion. And so we know, based on the principles of the vector triangle, that the third leg is the E to M, which is their course and speed. So if we now connect the dots like so, draw it out, and then extend that forward till we hit the line, you can see that it lands on 2, 3, 4, or like 234.5. And that is the, 234.5 right here. That is the true course of contact A. It's headed 234.5. Separately, because we're going to be working with multiple contacts here, we should label this A so we don't get confused, because we're going to have a lot of stuff going on in this triangle, or at the center of the scope. So this is the vector triangle for contact A, and it gave us a course and speed of, a course of 234.5. Now to find its speed, we have to measure the length of the EM vector. You can see it lands right at the 4, if not a tiny bit before the 4. So if you can do it in your head, you should know already what its speed is. But if we come over the 5-to-1 scale, yeah, it lands exactly on the 20. So the EM vector has a length of 20 knots. So now, if you had a separate sheet of paper, you'd write this down there, but I'm just going to write it on the page. We have a true course of 234.5 and a true speed of 20 knots. That is the actual thing that contact A is doing. And we'll get to why this is important later, but just before we continue any further, what you should do now is at M2 here, which is approximately where the ship should be right now, though it's probably taken you like 5 or 6 minutes to do all of this work since M2. You're going to draw a small diagram of contact A based off of its true course and speed. So if EM goes that way, then that means that the bow of contact A is pointing on 234.5. So if we draw that, you could imagine, it's approximately that way, that contact A looks like that. It's over there, it's going this way. But because we're also simultaneously going that way, those two vectors combine to give us a relative motion like so. But if we were to look out, because we're facing this way, if we were to look out on our starboard quarter, we would see the ship showing this aspect. It would be just about showing us a head-on view here, or its head-on view. So let's try the same thing now for contact B. Contact B had we'll carry over its relative motion. So we're going to do the same exact process. We measure out its DRM, set the triangle to be identical to the DRM, and then we slide it up to the R, and we draw it out this way. Remember, we drew the RM of A going that way because the DRM of A is going that way. But the DRM of B is going that way, so the RM of B should go that way. And now if we look back at our previous paper, you can see we got an SRM of contact B of 10 knots. So its relative motion vector should be 10 knots long. So we'll come over here, measure out 10, right there. We're going to place it there. Then we mark that point. And we'll label that M and make sure that this is clearly B's vector triangle. Now lastly, we're going to connect E to M so we could find the true course and speed of contact B. So we draw it out, connect the two, continue it all the way out. We get 2, 8, 3. So B has a true course of 283 degrees. And let's see what its true speed is. We measure out its length. It's a little bit over the 1. So on the 5-to-1 scale, you can see that gives you a little bit over the 5. Comes out to about 6.5 knots. So true speed, 6.5 knots. And now, because we have it facing this way as its EM vector, we can draw a little contact facing approximately the same direction. It doesn't need to be perfect, just generally the same direction, right there, pointing that way. So even though it's going to slide slowly behind us and pass this way, it's actually pointing in that direction. If we were to look at it, it would be, this is our ER vector, so it's just about on our port bow, and we would see its starboard aspect, whereas we're seeing the bow of contact A, we're seeing the starboard aspect of contact B. Now let's do it finally for contact C. So up here, there is the DRM of contact C. Line up the triangle to be perfectly in line with it. There we go. Gonna have to move this. We slide the triangle. It's gonna have to move it more. Sorry. There we go. As frustrating as triangles are, I still think it's better. They're better than parallel plotters because even the tiniest movement you'll be able to feel, and you'll notice when it's slid off. Okay, slide it down. I don't know if this is visible to you, but I can't get it any closer right now. I mean, I could have just flipped the triangle over. There we go. So after all those pains, I plotted R to M, or the RM direction onto the vector triangle again. If we come back here, we can see our SRM of contact C was 17, just about 17 knots, maybe 17.5. I think 17 is better. 17 knots. So now we're going to measure out 17 knots, or I guess we'll go just a tiny bit above it, like so, on our 5-to-1 scale, and we're going to plot it there. We mark that as M, and we make sure this is clearly contact C's triangle. And now we extend the line down. We continue it all the way to the compass rose so we can see that it lands at about 178. So contact C has a true course of 178 degrees. And its speed here is that. Comes out to 18. Or no, sorry, 13. True speed of 13 knots. Okay, now if we bring this EM vector over to M2, you can see that contact C is headed this way. So we're headed this way, and now on our starboard bow, we should see the port aspect of contact C. That's why this is important. Because now we don't just have a bunch of vectors moving around us on either side. Now we actually know what direction all of these ships are headed. And we can accommodate for, the rules of the road. We can figure out what our rules situation is. And B, we'll be able to go from here to actually manipulate our course and speed and see how that's going to affect things. Now, the one downside to the Navy method here is you can see how crowded the center of the scope is. And it's really hard to tell which R's and M's or which M's go to what if you didn't label it properly. A lot of people I've seen will bring colored pencil and they'll make each triangle a different color for that exact purpose. I never did that, I just labeled it, but it will get crowded here and confusing, and it's going to get more confusing soon. But before we go there, now we'll switch over to the maritime or the merchant marine method and compare the two.